Okay, so when there's no feedback, there's nothing really interesting. The coherence is kind of flat everywhere. But what happens is that if you put in negative feedback, for example, you start producing frequency ranges here and here, where the system transfers information more efficiently. This coherence can be related to bits per second in some crude way. Okay? If you have positive feedback only, information is transmitted very nicely here and here. Okay? And if there's a mix of the two, well, the two superimpose and you get a whole bunch of bumps. I'm not showing you that here. So maybe the feedback can be used to kind of set the range where you should do your optimal coding.
What do these frequencies depend on? The time constant delays or something?
Where the peaks are?
Yeah.
Yes, exactly. They depend on the time constant of delays and the synaptic time constants and a few other things, but those are the main ones. Okay, so we wanted to test this experimentally. Okay, go inside an animal, change the feedback. Well, first of all, see if there's a resonance somewhere, and then maybe change the feedback and see if it changes in the way you would predict. So what I'm going to show you is something that's happening right here. We're going to go from this situation, well, it's not clean. You can imagine cutting a feedback loop in an animal in a brain tissue. You're cutting a lot of things at the same time. Okay, so basically we're going to go from a situation where there's some feedback to no feedback. And this is, yeah. There's a refractory period in the model, yeah. Yeah.
So the frequency of the excited way. But when there is an excited, when it's positive feedback.
So when it's positive feedback, it doesn't run away because there's a refractory period.
So the frequency is determined as a refractory period?
Yeah. Well, these are the resonances of the coherence. So this is not a measure of the firing rate.
Yeah, okay.
So the rate is whatever the rate is. The rate is limited, and there is a refractory period in the model to limit the rate. And that's built into the susceptibility function for a perfect integrator. But that refractory period will have some role in where exactly these peaks are. But the main one is the value of the delay. That's going to be the main determinant of where your resonances are. Okay, so let's see what an experiment would look like. So this is done with our student Maurice Chacon, who's now a professor at McGill. He was able to change a situation that had a peak over here. Now everything is kind of on an incline like that because everything is kind of going down as a low-pass filter. The other one was much more broadband and you saw many peaks. But this one is everything kind of gets filtered out. But this one, as you cut the negative feedback loop, you go from this situation over to this situation. So this is an example of how you can manipulate a system and understand where it's maybe optimally transmitting information and what happens when you remove that. But again, it's not perfect. Okay, it's just messy. It's like when we cut that feedback loop with the drug, you don't get a nice peak that appears all of a sudden or it goes away. There's always these other loops around. Okay, how much time? I can't remember what time I started, but okay. This is an example that Axel talked about yesterday. I'm not going to say anything else about it. Here's a simple idea about noise-induced versus noise-suppressed rhythms. Okay, so we're talking about feedback loops again. And here's a simple picture where the activity is propagating in the feedback loop, but there's lots of noise. So how can these oscillations build up and how can they get suppressed? So here's an example where you have some kind of noise and some kind of input signal, and it goes into a threshold crossing device, your favorite integrated fire model or a threshold crossing, whatever you want, okay? And then the spiking output comes back into the input here with a delay. So this is what the noise looks like. That's the noise. This is what the sine wave looks like. That's the sinusoidal input. these two things together, actually, this plus noise gives you this. And every once in a while, this comes very close to threshold. And then that fires. So the firing is down here, but the firing propagates around the loop and goes and excites again. This excitatory feedback in this case, all right? So you can imagine that if this delay is just the right period, then if the spike happens here and it gets communicated to the next peak when this is high, it'll propagate forward in time and generate an avalanche of new spikes at every period. But if the delay here is not at the right period, let's say if it's half the period of the oscillation, then that's not going to happen. Okay. So these delayed feedback loops, they act as resonators. It's the same idea as what I just showed with these kinds of things. These information resonances. They're basically resonators. Okay? And you can calculate things, for example, as you vary the noise level, you can see how well this thing can amplify subthreshold oscillations. You can look at stochastic resonance or coherence resonance in these problems. And this is a classic thing. You can look at signal to noise ratio as a function of noise. This is without feedback down here, and with feedback, bang, you get this huge peak. You get these major oscillations showing up with the feedback if the noise is just right. So noise can propagate oscillations in these systems, but it can also suppress the oscillations. You have to decide if you're above threshold or below threshold. The threshold here has a slightly different interpretation than usual. It's if a spike goes around the loop, you want to know, is that spike going to cause a next spike? Or is it a bit too small? Or is it high enough to cause another spike? This is a simple model of an OTAPS. Most of you have heard about OTAPSs, but you can generalize this to a network if you want. Okay, so basically delayed feedback circuits just generate these oscillations. I'm going to say a few words about on-off cells and then about posture control, and we'll be done. So on and off cells, you've heard, luckily, from Michael Berry this morning. Some cells, when you turn the light on, they start firing. In other ones, they stop firing. So why am I interested in this? Well, because I didn't tell you the whole story. This business of oscillations, going around the loop in the fish, okay? This is basically only the top cells here, which are called